So having seen this computation with this new truncation operator Pn, we could express the ingredients of our finite systems here as follows. We could say that this n by n matrix is the leading and the only non-zero part of the operator or matrix Pn. And this right-hand side vector of length n is just the leading part of the infinite vector Pnb, which consists of exactly these entries and then followed by infinitely many zeros. Okay, so that gives us at least two ways to look at things. The first one is you say An is this n by n matrix, this finite section of A, and the space where this operator is acting on must be Rn, or well, maybe Cn. So just vectors of length n, arbitrary entries. Or you take this second perspective where you say An is what we computed as Pn before. So it's just this infinite matrix that, however, only lives on the top n by n corner, where it's exactly this matrix, and it's zero everywhere else. And this is acting on a space Xn of infinite vectors, obviously, being an infinite matrix. But again, these only live on the first n components. Let me abbreviate this like we did before. So every star represents a free variable that is running around the real or complex numbers, and we have n of them, and then all the rest has to be 0. So in this first perspective, it's clear what invertibility means. And I mean, in the second perspective, it's also clear that you cannot seriously talk about invertibility of this as an infinite matrix, because it has all these zeros here. So we must be talking about invertibility as an operator from this space Xn into the space Yn, which is just the same, and which is all about the first n components, and therefore all about this top n by n corner of the matrix. On the other hand, in the second perspective, it's pretty clear what it means that Xn is contained in Xn plus 1, and all of these are contained in X, which is just LP, because by construction this is just a space of infinite vectors, so this is always a subspace of X. And I mean, you could not say that R2 is a subspace of R3, which is a subspace of R4, and so on. At least not immediately when you write down vectors just as 2 vectors, 3 vectors, 4 vectors. You could only do this after interpreting one as somehow embedded into the other, which is pretty much what you're doing here. And the other thing that is also easier to see in the second perspective is the convergence An to A. How could you understand that? I mean, we're talking about a sequence of infinite matrices converging to an infinite matrix. It's not so obvious here, right? Here you're talking about a sequence of finite matrices that get bigger and bigger as n gets bigger, and so in what sense would they converge to that infinite matrix here? Not so clear. Okay, we just spoke about how to fix all these problems. So for example, in the second perspective, you can talk about invertibility, but of course you always have to remind yourselves that you're not talking about operators from X to X, LP to LP, which would look at the whole infinite matrix, but only as operators on these subspaces Xn and Yn here. Okay, and up here, if you want to write something like Xn is contained in Xn plus 1, That would certainly need a special kind of embedding before you can say the plane is part of the 3D space. And similarly, if you want to talk about strong convergence here, then of course at first glance you run into trouble, because A goes from x to x and an goes from xn to xn, which doesn't match. So what you have to do here is squeeze a little pn in between, which is bringing you down from x to xn, and from there an is taking you again into xn, but that's just part of x. So now, just like here, you can also understand this as an operator from x to x, and that resolves the problem. Okay, so I mean, both perspectives have their benefits and their problems, and what we often do is we freely switch between these two perspectives, and sometimes as some kind of compromise, we take a third perspective. So we copy our second perspective, but instead of these zeros down here, we put ones. So we could also say we take that finite n by n matrix, and instead of extending it by the zero operator, we extend it by the identity operator, thereby making the whole thing invertible, at least giving it a chance to be invertible, which it is as soon as this n by n matrix is invertible. And now indeed we can treat this as an operator on the whole space x of infinite vectors. It's not finite rank anymore, otherwise it couldn't be invertible, but I mean, hang on, it's just finite rank plus identity, and who cares about that identity operator? You don't need to store that on your computer, right? So if I label that little finite section here by bn, then an is invertible as an operator on all of x, if and only if bn is invertible as a little n by n matrix. And now it's clear that all these spaces are contained in one another. They are even all the same. And because all operators are acting on the whole space x, it's also clear what strong convergence means. It's just the usual way of strong convergence. There's only one space x that you have to talk about. And solving your little equations, an xn equals bn, is essentially solving the n by n system in the top corner. I mean, there is not much to solve when the rest of your matrix looks like that. And also for stability, you can freely switch between the sequence an like this and the sequence bn like that, because the inverse of an is just the inverse of your n by n matrix bn extended by the identity. You can say that the norm of your inverse is just the norm of the inverses of these n by n matrices, or it's 1 if that is bigger. So it's the maximum of these two, and this is just a block diagonal matrix argument, just like you're using for non-block diagonal matrices in problem 14. So what I'm saying here is that this is staying bounded if and only if that is staying bounded. So indeed, this sequence of infinite matrices is stable if and only if that sequence of finite matrices is stable.